Welcome to today's skill workshop on the HiSim household infrastructure and building energy simulation tool. This session is hosted by me, Noah Pflugert from Forschungszentrum Jülich, and Johanna Gangelbauer from Forward Energy. Now, first, what is HiSim? HiSim is an open source tool written in Python for house infrastructure simulation for modeling electricity, warm water, and heat, both for generation and consumption. But why, you might ask? Aren't there tools for that already? Which is an excellent segue to the Y project, which is a European Union project which has the motivation to better understand how interventions affect the load profiles of customers. And part of that was performing bottom-up simulations of households and people, bottom-up simulations of household infrastructure, then simulate reference cases, and then simulate interventions and compare how the interventions change the demand profile. Important first step on that was understanding the households better. But before we get into that, I first want to briefly introduce to the agenda. First, I'm going to introduce you to household types, say a few words about HiSim works, show a couple of example results that should take about 20 to 30 minutes, depending on how many questions you ask in between. And then Johanna and David are going to go to the HiSim Colab example, where you can mess around with the simulation tool itself. Given the very limited number of participants, I think it's fine if you just raise your hands and ask whenever you have a question. Let's make the entire thing a little bit interactive and not just me talking to a black screen. If you have any questions. If not, I'll assume I explained everything perfectly, which is good too. Okay, then let's get to the household types. For household types, we collected pretty much all publicly available smart meter data sets. And then a colleague from the University of Deusto analyzed them in detail, selected the 25 usable data sets for analysis, which gave us about 25,000 individual load profiles. We discarded the small data sets, the short time series, the submetering, and all these things. And then they clustered the data and started analyzing things. And clustered the data and tried to identify personas. And I would like to show a few results on how different consumers are and why a detailed analysis is so important, why a simple standardized load profile will not yield useful results in many cases. For the visualization, we used the heat maps. They work like this. You have the time on the y-axis. It starts from 0 hours to 23 midnight. And then on the x-axis, you have the months or the days of the year. So every column here is one day. And you can see here in the middle is the summer. On both sides is winter time. You can see here very vaguely the pattern of how they tend to use more electricity in the evenings in the winter and all these things. You can also see when the people are getting up. They are typically getting up between 6:30 and 8:30, because that's when the electricity demand starts. Now, to first introduce some typical behavior, or typical types of households that we found. The one big difference is if the people do anything different on weekends, or if they don't change their behavior on weekends. So if they change their behavior on weekends, that points towards the fact that they go out during the week mostly for work, while some people are either in home office and stay home all day, or they are unemployed, or have some other reason to not change at all during the weekends. Here you can see on the right, you can see two contrasting patterns. One is where the energy demand increases in the summertime. That points towards air conditioning. And the other one where the energy demand decreases in the summertime, which points towards electric heating in the wintertime primarily. And definitely no air conditioning. Then you have different types of behaviors during the day that you can see on the left side. You have people, especially interesting is that you can see the meal times in the demand profiles. So here in the middle, upper middle, is a pattern of somebody who has breakfast at home has lunch at home and cooks dinner at home. At the bottom, you have somebody who doesn't come home for lunch, or a family who doesn't come home for lunch, but cooks breakfast in the mornings and maybe sometimes in the evenings. While here on the left, you have people who either don't eat breakfast or don't eat warm breakfast. Once without lunch and once with cooked lunch. So you can see already that there's big differences in the energy demand profile. What we also found is that there are a surprising number of secondary residences where people only go on weekends or during summer vacation. One case on the left here is a case where they go also on weekends. On the right is a case where they basically only go during summer holidays. That might be a foreign-owned residence in Spain, for example. And of course, there's offices and businesses which have very different load profiles, which is basically the inverse of the earlier residential profiles. So they show up somewhere between 7 and 9, then they work all day and then they go home. And you can also see, for example, Christmas here on the right. Nobody's going to work on Christmas. So in summary, if you study interventions, if you're trying to figure out future load or if you're forecasting, always consider the load pattern. If you, for example, want to calculate a PV system or a battery or heat pump for holiday residents, then your economic results are going to be very different than for a normal home, for example. And if you don't consider the demand profile properly, you're going to have unhappy customers or wrong results. To perform these studies in detail, we designed HiSim as a scalable, free alternative to do large-scale simulation studies for thousands or tens of thousands of households without needing to worry about licenses, because HiSim has an MIT license, without C++ or Java or Fortran programming. If you've ever worked with transfers and enjoyed the Fortran code over there, then you'll really appreciate that HiSim is 100% Python and easy to extend. We wanted to have a solution where we don't have to worry about 30 or more years of crafted and bolted on features that might or might not work. So HiSim is strictly object-oriented and was written from scratch only a couple of years ago. And we wanted to make sure that it's very easy to extend, that we can have master students and to write new features or to write new components, and that they are productive within weeks. And so far that has worked out really well. Now, how does it work, or what does it do internally? It's a time step simulation. So it splits the year into discrete time steps, and then does a simple forward pass. It's component-based, so every component has inputs and outputs. Every component has a configuration. The outputs can be connected with inputs, and then HiSim iterates inside every time step until the outputs stop changing. Any questions so far? No. Okay, perfect. Here's an example for a house configuration. You have occupancy, so what the people that are living in the house are doing. You have weather. The weather and occupancy influences the building. You have the PV system. You have electricity base load, which is influenced by what the people are doing. You have the heat. You have the controllers that control the heating system. You have a heat distribution system. You have heat pump, and so on. All the connections are fully customizable. So when you define a house, you can obviously connect the weather with the heat storage if you want to simulate the influence of having your heat storage outside and have a different ambient temperature, but you don't need to. You can add new components at any time. So if you have the idea of adding an electric car or a second electric car or a third electric car for the very rich people, then you can just add more components, connect them up, and it just works. One nice feature is that you get all these charts and everything automatically generated, so you don't need to draw them by hand. As components, we decided to have two types of components. One is the physical components, like which model things that you can actually touch, like a heat pump or a water storage or a house, and you have the logic components or the controllers. We try to keep those two strictly separate to make it easy to test different control algorithms or create new ones while keeping the physical components constant. To make it easier to test, for example, demand-side management, which, as you probably know, will most likely significantly change future demand. And we designed HiSim, or one of the design goals was that we want to very much be able to quantify how implementing different types of demand-side management on a large scale will influence the future demand. Now I would like to introduce a selected number of physical components and how we implemented them. For heat pumps, we are using the HPLib, which uses a regression of real heat pump measurement results, and then basically gives you the efficiency and the temperatures if you that will come out if you feed in water at a given temperature. For the building, we use a 5R1C, one zone model. It's based on the RC simulator from ETH, but it's been extended to allow sub-hourly resolution and also has a bunch of additional features like heat demand calculations things. For PV, we have a component based on the PV-lib from NREL, which is very nice because we can just use all the measurement data from NREL and don't need to do our own PV system measurements. And the PV-lib is very well validated. For weather, you can just feed in any weather profile you like, basically, as long as it's in correct format. For occupancy, we are using the load profile generator DE, which is a behavior simulation tool that has been developed by me and has been out for more than 10 years now, and has a whole bunch of predefined different households, like a single family with and without children and so on. It's been calibrated for Germany, but it's been widely used for other countries too. What we don't have yet is an integration of the household types that I showed earlier that we still have to implement. You can add, as a not so physical component, CSV files or any time series you like. And also we have things like smart devices or electric cars that get charged according to incentive signals, and quite a few more. We're currently working on the entire fuel cell and electrolyzer side, together with colleagues that are doing actually fuel cell research. So that should be out soon too. For the controllers, our design goal was to make things extendable but flexible. So we split the controllers in level 1 and level 2 controllers. Level 1 controllers control a single device, for example, a heat pump or a battery. The level 1 controllers take care of all the physical constraints or the device constraints. For example, you put in the minimum run times or the schedules. You program the level 1 controllers to keep a water tank at a certain temperature or in certain bounds and other things. And then there's the level 2 controllers, which set incentive signals for the level 1 controllers. For example, an energy management system that can use the smart grid ready interface on a heat pump to set to run if there's excess PV energy. But the level 2 controllers can't override the device constraints. So, for example, heat pumps, as you probably know, it's important that you don't turn them on and off too quickly. So you don't get too many cycles, because otherwise you break them pretty quickly. So the minimum runtime and the minimum off time you would put in a level 1 controller, and the level 2 controller then gets hooked up to the PV system and sends a smart grid ready signal to the heat pump controller to say, hey, now you could heat a little bit more if it's possible. Level 2 controllers are also have the design goal to prioritize energy and, for example, ensure that the car gets charged before any excess energy gets dumped into the water tank or into the building itself. To make sure that there's a sensible processing of the energy. Now, how does it work internally? As you might know, real systems frequently have circular dependencies. So The flow rate of the heat pump depends on the temperature of the house. The temperature of the house depends on the flow rate of the heat pump. And in reality, these things tend to slowly adjust over time. But we wanted to make sure that it's no. In simulations, you can use the same approach as in reality. You just have a fixed simulation step. The shorter your simulation time step, the easier it is to use the same approach as in reality. If you want to use larger simulation time steps, like a couple of minutes, 15 minutes, an hour, then it becomes important to iterate inside a single time step and have these circular dependencies properly implemented. So HiSim enables circular dependency by doing iterations in each time step. And for that, we're using a simple substitution solver. The first component basically does whatever it likes. Then the second component gets the outputs from the first. Then the outputs from the second go back to the first, and then you iterate until it converges. In some cases, you have fluttering in the controllers, and then there's a special switch that tells the controllers to please stop fluttering, and then it usually converges after a couple of iterations. But all in all, it works very well. I did not come up with this. This has been invented like 40 years ago, and it's been working ever since in all kinds of different simulation tools. Other than that, some more noteworthy information is that we are using a default time resolution of 1 minute. Depending on how complex your model is, the calculation times on desktop machines for 1 year in 1 minute resolution is usually 1 to 5 minutes. Some of the models take quite a bit longer, depending on, for example, the heat pump model. We have 2 different heat pump models. One is vastly more detailed than the other, and the more detailed one is considerably slower so far. So we still need to optimize that a bit. HiSim is very easy to automate. It's fully scriptable either via Python or via command line. It's suitable for mass simulation, and we included a reporting engine to automatically create detailed analysis of the results. And we are doing economic calculations, which are currently a work in progress, but they will probably be fully put in the next couple of months, so that it will immediately, it has predefined prices for everything, and then it will tell you how the cost, both for energy and for invest and OPEX, was affected by whatever the changes you did to the model. Now, brief introduction to some of the results before Johanna gives you the workbook to play with, where you can see all the results. For the results here, we simulated a German single-family home, which got a 10 kilowatt peak PV panel. It has a heat pump and a self-consumption rate of only 21.9% and an autarky rate of 24.6%. So you can see the household is net zero, basically net zero, but it still only gets about 25% of the energy from the PV system, and all the rest is first put into the grid and then later withdrawn into the grid, because a major part of the load is from the heat pump. And the PV system primarily generates in the summer, and the heat pump primarily needs energy in the winter. So that also shows why detailed simulations are needed. Now, some results of how things look. Here on the left side, you can see the energy demand of the residents. This is an output from the load profile generator. You can see they have vacations twice a year. A couple of nights they stay up very late. You can see Christmas over here. And all in all, it looks like a typical residential load profile. On the right side, you have the PV system electricity output with the typical I shape. And it generates most of the energy in the summer. Now, what kind of thing can we do with the controllers? On the left side, you have just normal ping pong control. So the heat pump turns on if the house gets too cold, and turns off when the the water that's coming back is warm enough. And on the right side, you have the same thing basically, but with smart grid ready control enabled. So the heat pump turns on when it's too cold, or it tries to overheat the house a little bit if there's excess PV energy. Then you can see that starting from about February, in the winter months, it doesn't do much, but starting from about February and until about middle of November, it shifts a significant part of the energy demand to the day. And in the evening, there's not a lot less energy demand needed for keeping the house warm. So that significantly increases self-consumption. That will also be probably going forward very interesting for a lot of single-family houses to increase efficiency of their own system. We can also do batteries. On the left side, you see the charge and discharge signal for the battery. So during in the mornings, it charges, in the evenings, it discharges, and then you can see here the state of charge. As you can see, the basic problems of residential batteries is that in the summer, they're pretty much always full, and in the winter, they're pretty much always empty. So it doesn't make much sense to have them cover more than a single day or single night of capacity. You're not going to be able to, with a residential battery, cover days or weeks of energy demand. Here you can see the values from the thermal buffer storage. On the left side, you can again see if with the smart grid ready control, how much the energy demand gets shifted to the day by the smart grid ready implementation. And on the right side, you see the average temperatures in the storage tank. You can see in the summertime, it's just not used and slowly cools down completely. And that's it with the introduction to the result, to the HiSim. Yes, Robbie.
Yeah, you talked about the circular dependencies which operated within, I'm going to use the word sovereignty, one controller sovereignty. But what happens when you have different control sovereignties, if you like, interacting? How do you come to a satisfactory solution under those circumstances?
You mean if there's one controller that tells a second controller something, that tells a third controller something?
Yeah, and they're one is not above the hierarchy in that sense. So they all have their own, you know, their own minds, if you like.
What we do is we give them 10 iterations time to figure things out themselves, and then we tell all of them, please stop and use whatever was the latest thing you decided on. And that works surprisingly well. So there's no hierarchy or anything, but just simply, please stop. Any other questions? Doesn't look like it. Nothing in the chat either. Then, Johanna, you want to start sharing? You are muted.
Thank you. So before I start to share my screen and show you the Google Colab, you should find a link in the chat where you can go to the Google Colab yourself. And then you can create a local copy of the notebook in your Google Drive so that you can try out the stuff yourself. And as yes, Johannes?
Sorry, no, I'm a bit late. I know. One question. Thanks. It looks very interesting. I have, let's say, two questions. One is, so for which countries, I mean, I saw at the beginning you had a couple of countries mentioned, which countries you have so far, let's say, used any of these smart meter data? And secondly, so this is all data coming purely from the I mean, is there any kind of socioeconomic variables of these households except for, I mean, have you kind of other data in some surveys, or is it somehow possible to link that data of the households to, let's say, country panel studies? I mean, is there any? So
Yes.
what information exactly do you have on a household except for their very detailed data that you showed on load profile and over time, etc., which is very detailed, of course.
Okay, so there is some of the data sets include socioeconomic parameters. And inside the Y project, we also released a new data set from a Spanish cooperative with 25,000, I think 25,000 smart meters, which is already on Zenodo. You can find it if you look for the Y project in the Cordis and look for publications. About the socioeconomic factors of the load profiles, we did the analysis, and there's a publication that's been submitted but not approved yet. And that goes into much more detail about what factors influence what. If you want to do your own analysis, I think we somewhere have the list of all the data sets that we used, and then you can look at them in detail. Just shoot me an email, and I'll look for the list of the raw data for you.
Okay, great. Thanks. Thanks.
Sure.
Okay, nice. So I will step back into the Google Colab. And my first question is, did every one of you manage to go there? Perfect. So as we are not so many, I think that you can just, if you have any questions, come up with it, raise your hand, post the questions in the chat, whatever you feel like doing, because it should be interactive. And before we really go into the coding, I try to give you an overview on what I'm planning to do. So we kind of implemented the HiSim code to the Google Colab, and I will try to show you 3 examples. So the first example is a really simple example with random numbers, where I basically just want to show you how to create components and connect them, and what the outputs of the simulation can look like. In the second example, I would like to do a household simulation where we simulate a simple household with heat pump and PV panel and create more or less the plots that Noah showed you before. And then finally, I will introduce you to the modular example. This is a bit more complex than the basic household because you can configure the technical configuration as you wish. So you can do parameter studies with it, and you can also choose to have either this load shifting control or not. And this is where I think that we will spend most time with, or this is also the thing that you can try out afterwards to make some simple studies or look at the stuff. Good. So the first thing that you need to do is to install HiSim from PyPy. So HiSim is Python code. You can find that on GitHub. But as we need to have access to all the functions, modules, and classes implemented there, we just download it from PyPy. This will take some seconds, and then you will need to restart the Google runtime. I think I will just wait the 3 seconds it takes. Then the next step will be to import the most important modules from HiSim, which is the simulator, the simulation parameters, and the post-processing options, and some other stuff that we need. Usually it's a bit quicker, but I ask you to be patient until all the packages are loaded, because otherwise we cannot run the examples. Okay, so now I think we can go into the first example. And in the first example, we have we want to create three components, 2 random numbers and 1 sum builder, which just sums up the 2 random numbers. So we have this function where we get the simulator and the simulation parameters as inputs, and then we start creating components. So the random numbers we imported from the from PyPy, from the HiSim, and we create first 1 random number which ranges from 100 to 200 and adds the component to the simulation. One important question, do you see my mouse?
Yes.
Perfect, okay. That's very good to know. So we create 1 random number which ranges from 100 to 200, and then we create the second random number which ranges from 10 to 20, adds the component to the simulation, and then create the sum builder. And here we connect the output of the random number with the input of the sum builder. So the first input of the sum builder with the first random number and the second input of the sum builder with the second random number. Okay, so here we just defined the function which is called first example. And in every example we have 3 blocks. So first of all we define the function, then we run the simulation based on the function, and then we look at the results. So once we have defined the function, what we already did, we can run the simulation. I just started now because it will take some time, and then explain you what we do. So first of all, we define simulation parameters. Here we want to simulate 1 year. We choose 2019, and we have per default 1 minute time resolution, so 60 seconds per time step. And then you can also add post-processing options to the simulation parameters. And in this case, I would like to show you carpet plots, which are more or less the charts that you saw before in Noah's presentation with the nice colors. And here I tell the simulation to create those plots. Then it's important to set the result path. So we indicate the name of the setup function, which is first example, and add a variant name first test. So we can, this is the location where the results of the simulations are saved to. And this is the words we use to set them. And with the simulation parameters set and the simulator set, we can run the first example and tell HiSim to run all time steps. So I already executed the code, and now you can look on the left side, you can look at your files. And here you see that we created 1 directory, which is called first example, and it contains 3 subdirectories. Each component has 1 subdirectory. So the random numbers from 10 to 20, the random numbers from 100 to 200, and the sum builder. And now we can go to the third block where we look at the results. So what we do is we tell the Google Colab which folder we would like to look at, and we search for a folder with the string first example in it. And then we loop over all subdirectories, and if we find a carpet plot, we just tell Google Colab to show it. So this is what we get. We have the first random number, which ranges from 100 to 200. So as the plots before, this is a carpet plot. So from left to right, you see the day or the month or the season. And from up to down, you see the hour of the day. And as it is a random number, it looks like a random number. So the color indicates the scale. And on the right-hand side, you see the scale. So in this case, the random number ranges from 100 to 200. The next plot is basically the same. It's also a random number, just that it ranges from 10 to 20. So on the right-hand side, you see in the axis that it ranges from 10 to 20. And the sum, of course, also looks the same because we just add up random numbers. And in this case, the scale ranges from 110 to 220 because we sum together the two random numbers. So this was more or less just to show you how to set up components, how to set up the simulation, and what kind of carpet plots come out. I will just go to the next example, and if you have any questions, you can just interrupt. Okay, so the next example is the basic household. And here we simulate a system with weather data, with an interface to the load profile generator to get the electricity consumption and hot water consumption profiles, and also internal heat gains. We have a building component, a PV system, and a heat pump with its controller. And as before, first of all, we have to define the example in the basic household explicit function. Then we have to execute the function with the simulation parameters. And finally, we can look at the results. So in this case, the definition of the function itself is, I would not say more complicated, but it contains more components. So here we have the building component, we have the occupancy component. Occupancy is the load profile generator. Then we have the weather component, the PV component. We also have electricity meter, which in each time step sums production and consumption, or sums and subtracts, so that you know the available electricity in each time step. We also have a heat pump controller and a heat pump. And then we need to connect all the components. So for example, the photovoltaic system needs radiation data in order to compute photovoltaic power. Of course, the electricity meter needs to be connected to the electricity production of the PV system and the consumption of heat pump and occupancy, and so on and so forth. And finally, we need to add all components to the simulator. Okay, so I have to execute the code so that also Google Colab knows what the function looks like. And then we can already start the simulation. I start it first and then explain because it takes some time. So as before, we need to set the simulation parameters. We want to have a full year. And this time we take a time step of 15 minutes because for the carpet plots that we want to look at, 15 minutes are more than enough to see what's going on. As before, we set the post-processing option for plot carpet so that we see the nice colorful charts. And in addition to that, this time I want to create a PDF report and add some sub-functions for the creation of the PDF report so that everything is in there. And I would also like to create network charts to show you which components are in the example and how they are connected. And this time I call the variant name second test because it's the second example and the setup function is the basic household explicit. This is what we will find in the results folder afterwards. So once simulation parameters and simulator are defined, we can just run the function, the basic household explicit I explained before, and run it for all time steps. So right now the simulation is already finished. The Google Colab is creating carpet plots, and in some seconds it will be finished. And then we can look at the results. When we look at the results, the code is similar to before. There's just one block more to show the carpet plot and one block to download the report. So the simulation is finished. So I can show you the results. It takes some time to create all the plots. So the first thing that you see is the system chart, where you see all the components that we configured and how they are connected. So for example, we have the weather, which is sending radiation and temperature data to the PV panel. It's sending temperature data to the heat pump because the efficiency or the coefficient of performance depends on the outside temperature. And it sends temperature and radiation data to the building in order to compute heat losses and heat gains, solar heat gains. The occupancy provides the consumption values to the electricity meter, and it provides internal heat gains to the building. The PV system also provides the production values to the electricity meter, and the heat pump also provides consumption values to the electricity meter. And the heat pump controller gets the temperature of the building in order to know if the heat pump needs to be activated or not, and then sends the control signals to the heat pump. And of course, the heat pump tells the building how much the building is heated. So this is what our system looks like. And now, so maybe I just show you what kind of results we have first. So this time the results are in the folder Basic Household Explicit, second example. And for each component, we have a subdirectory containing all the outputs. And each of the outputs has a carpet plot. And what Google Colab does, it just plots all the carpet plots that are inside all of these subfolders. I think we won't look at all the carpet plots, but it makes sense to show you some of them. So for example, here you have the water consumption of the load profile generator. Again, from left to right is the day of the year, and from up to down is the hour of the day. So during the night, we don't have water consumption, but the pattern itself is not so much influenced by the season. And we see two stripes here. This is when people go on holiday and don't need warm water. This is maybe not so interesting. This is the electricity output of the load profile generator. So similar to the hot water, during holiday, they don't need electricity. During the night, they don't need so much electricity. And you see that in the morning, there is always electricity need, in the evening also. And sometimes at lunch, there is also a peak load. And I didn't notice that it was Christmas before, but you can also see Christmas here with a really high electricity consumption.
I would like to, sorry.
No, just.
Okay, I would like to add one interesting detail that I learned over the years. This is a German profile, and you can see that the German profile has peaks of about 6 to 8 kilowatt. Spanish and Italian households, for example, they are usually hooked up with one 3.6 kilowatt link only. And so the profiles don't quite fit because you can't turn on that many electric devices. The Germans are cooking, for example, with electric oven and using cooking two different things at the same time, and turn on the water cooker, and already you're at 6 or 8 kilowatts. While in Spain or Italy, that simply does not work. And then for that, you would need to spread out the load a little bit more. Just an interesting side.
Now I feel bad for cooking every day and creating so much electricity consumption. Okay, in the load profile also provides us an input for, or an output for the internal heat gains of the devices, which is nice for the building simulation, and the internal heat gains of the people. So depending on if they're home or not and what they're doing, they are radiating heat waves. So I think this is not so interesting. La, 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 la. Here we see the heat pump and the heating of the heat pump. So this is the thermal power of the heat pump, and this is the electrical power of the heat pump. And of course, as we have a coefficient of performance of roughly 3, the electrical output ranges from 0 to 2 kilowatt and the thermal to 7. So heat pumps are efficient in that sense. So here we can see the weather data, so radiation data, more radiation data, solar, what the sun is doing data, also the temperature. Of course, winters are colder and summers are warmer. And here we can see the temperature of the building, which during the winter ranges from 19 to 23 degrees, and in the summer it gets hotter. Yes, I think this was the most interesting plots. Oh, and here is the PV generation, which, as Noah said before, in the summer is stronger and in the winter is weaker. And of course, we don't have any production during the night. Okay, so what we can do is we can have a look at the report, but I have to reshare my screen, otherwise you won't see the PDF. So I just show the entire screen. I think it will be easier. And we can look at my downloads. So I downloaded a PDF report. And the PDF report contains a chapter for every component. So for example, for the simulation parameters, of course. So for example, for the occupancy, we see that we use the occupancy profile 1, which is called CHR01 in the load profile generator. And we are located in Germany. So you can look at the configuration of every component. And in the end, we have a list of KPIs that are evaluated. So KPI stands for key performance indicator. It's just how to say values of relevance. So for example, we have the sum of the consumption, which is roughly 3,000 kilowatt hours in that year. We have the sum of the production, which is 12,000 kilowatt hours in this year. So we have quite a lot of production and not so much consumption. And we see the self-consumption value, which is 1,300 kilowatt hours. And the self-consumption is the amount of PV production that is used by the household itself. Then we have the injection, which is, of course, just the difference between the production and the self-consumption. And we can look at autarky rates and self-consumption rates. So the autarky rate is the self-consumption divided by the consumption. And the self-consumption rate is the self-consumption divided by the injection. So it's always the percentage of self-consumed energy. In the first case, it relates to the total consumption, and in the second case, to the total production. Okay, so this was the PDF report. I just keep on talking, and please interrupt me if you have any questions or something remains unclear. Okay, if not, then we can go to the last example, which is the modular household. And the modular household from the setup itself is similar to the basic household. The main difference is that the function, here we go. The function has an additional input, which is called household config. This is either a JSON file or a JSON data class, where you can indicate what your household should look like. So for example, if you want to consider PV panels or not, if you want to consider batteries or not. And then the example, based on the values that we set in the household configuration, sets up the components and connections automatically. This is very nice because then you don't have to write a function for each configuration, but you can just use this function for many configurations and make parameter studies and analyze some stuff. And what I want to do today is to run this example once with the load shifting control activated and once without the load shifting control activated. And then we can look at the differences. If you want to experiment with this afterwards, you can also try different things. For example, try different PV sizes, try different battery sizes. Yeah, just experiment with it. So first of all, as before, first we need to define the function. I won't go into detail. It just sets up the components and connections that we define in the household config. So once we define the function, we then set the household config and run the example or the function. And finally, we look at the results. And this time for executing the function, more or less we do the same as before, just that in addition, we need this household config. And to define the parameters in the household config, first of all, we download the default configurations from the HiSim that we got from PyPy. And the household configuration sets up by two different configurations. So we have the archetype configuration, which represents the initial situation, and we have the system configuration where we define the technical equipment. So in the initial situation, in the archetype config, for example, we define the type of building. This comes from the tabular database. I don't go into detail, but if you have time afterwards, there is the link above, so you can have a look at this. For now, we just simulate a German building. It's a single family house. So I would say a normal German single family house. We can define the area of the building if we are not fine with the default values of Tabula. And we define the heating system which is initially used, which in this case, I define to be district heating. So I can make my screen bigger, far better now. Okay, so this is the archetype config. This is more or less the initial situation that you cannot change. So once you live in a German single family home, of course you can move, but in this situation you cannot change anything. And then we have the system config, and these are the things that you can, how to say, upgrade, change, install, and you can work with. So for example, you can choose if you want to have a PV system included or not. In this case, I said yes. So I set the parameter true, and you can indicate the power. In this case, it's 8 kilowatt peak. The same is for buffer storage. You can decide if you want one or not and what size, battery. And for the heat pump, you can indicate if you want to change the initial heating system or not. And in this case, I say, yes, I want to change my district heating with a heat pump and just see what it looks like. And then we have some parameters for combined heat and power, fuel cells, hydrogen storage, stuff like that. But I won't go into that today. So for today, I would like to experiment with the surplus control and simulate the example once with the surplus control considered, so with load shifting, and once without load shifting. I already ran the examples before. Okay, it just jumped. So I already ran the examples before, but I ran it once without surplus control and indicated in the file name here, no smart control. And then once I set this parameter to true and indicated here with smart control. I ran it before because it takes some time and I didn't want you to wait for the results, but you can just experiment it for yourself. And what I also did is that we include smart devices, which means that everything which is used by the occupants of the load profile generator, which is washing machines, dishwashers, and dryers, can be shifted in a given time frame so that we can do load shifting also with these devices. For the simulation parameters, we have more or less the same as before. So we chose a time step of 15 minutes. We want to see carpet plots. We want to see network charts, and we want to generate the PDF report. Okay, so you can run the example. It will take some time because you need to wait for the answer from the load profile generator, which calculates the profiles in a cluster in Spain. But after some minutes, you will get the results. And as said before, I already executed the code once with smart control and once without. So here you see the two folders. And now we can look at the results. So to look at the results without smart control, we have to choose the right name here. So we search for a folder which is called modular household explicit, no smart control, or it's not called like that. It contains this string in the name. And then as before, we plot the network charts, we plot all the carpet plots, and we download the report. Need some time to execute. Okay, I stopped the simulation above just to be able to look at the results. And I can do it because I already calculated it before. You have to wait, of course, until you have the results available. Okay, so first of all, we can look at the network chart. So the occupancy is called UTSP connector in this case because we use the universal time series provider to reach the load profile generator, which runs in Spain. The occupancy is connected to the building, to the train hot water boiler, and to the electricity controller. The building needs internal heat gains, the boiler needs the hot water consumption, and the electricity controller just counts consumption and production and needs to know the consumption value. Then we have two heat pumps with controllers, one heat pump for hot water, it's called DHV heat pump for the DHV boiler, and one heat pump for the heating of the building. And we have a PV system and weather data. And here on the right-hand side, you see the smart devices. So we have one dishwasher, one washing machine, and one dryer. And I think it makes sense to look especially at the profiles of the devices that can be shifted by the smart control. So here you see the dishwasher, and this is the result without load shifting. And you see that the dishwasher runs a lot in the evening, so between 6 and 8 o'clock, and also in the morning and during the day. We have the washing machine. It's a bit more difficult to see, but similar to the dishwasher, it runs a lot in the evening, so between 6 and 8, and we have some spots during the day. And also the heat pump profile will be interesting. So here we have the electricity output of the heat pump, and it runs primarily at, I would say, 5 to 6 o'clock when the people need hot water, and also in the evening between 5 and 8. So I think this is enough to just show you the difference. So when I execute the code, now for the second call where we used smart control, I changed the name to the folder with the string modular household explicit with smart control and execute the code again. And now we can see in the system chart that the electricity controller does more than before, because it does, for example, not only empfangen, it gets signals from the smart devices and it also sends them back. So, for example, when surplus electricity is available, the energy management system electricity controller here tells the dryer to please turn on because right now there is PV surplus available. The same holds true for the washing machine and the dishwasher. And also the heat pump controllers have can receive signals from the energy management system which tell them to preferably heat or not, depending on if there is PV surplus available or not. And when we look at the profiles now, for example, the dishwasher, which previously had a lot of electricity consumption between 6 and 8 o'clock, now runs primarily during the day whenever the PV system is producing energy. And the same holds true for the washing machine. Of course, especially in the winter, the surplus control is not always working because there's not sufficient PV surplus available. But in the summer, the washing machine runs primarily during the day. So this means that load shifting is working. And then we can look also at the DHV heat pump, so the electricity consumption, which had 2 bars, one at roughly 6 o'clock and one in the evening before, is now running primarily during the day. It completely works in summer where the DHV heat pump just runs with electricity from the PV system. And in the winter, again, it's not sufficient to run just during the day. So sometimes it has to be activated during the night because there's just not enough electricity available. I think this was the most interesting charts. You can do the thing yourself and look at every output, but I think it does not make sense to discuss all of them. What I would like to finally do is to show you the reports and compare them. So we have, so the Zoom window is kind of annoying. So I just try to place them next to each other. Yeah, first report, second report. Okay, so it took some time, but now we see both reports. On the left-hand side, the results or key performance indicators without smart control, and on the right-hand side with smart control. And we see that the consumption is more or less the same. It's a bit higher in the case of surplus control because we put more energy in the boiler, and therefore we have a bit more heat losses and need a bit more electricity. The production is exactly the same. Of course, the PV production does not change by indicating a different control. And the self-consumption is higher in the case of load shifting, roughly about 300 kilowatt hours, which we managed to shift. And the injection is a bit smaller. So the injection is smaller by the 300 kilowatt hours that we managed to consume ourselves. And this means in terms of autarky rates that we can rise the autarky rate from 20 to 24% and the self-consumption rate from 21 to 25, more or less. So this is the kind of things that you can do with HiSim and especially with the modular example. We can try different configurations. We can try to use a battery, but I think the most, how to say, I think the best thing is that you just experiment yourself and we stay there. And if you have any questions, you can just ask them.
Or if you don't want to experiment and you got a good impression, everybody can just leave. That's also up to you. We don't have a GUI yet regarding the question in the chat. There's one planned. I'm just looking for money, basically, to get the GUI, to get some GUI programmers. Other questions? Yes, Robbie.
I'm a bit interested about whether the Amorous project and this project have some similarities, and whether you see yourselves including agents, agent behavior, or on the other side, Amorous including more household characterization.
Well, the load profile generator itself is an agent-based behavior simulation. I talked with the Amorous people at the Open Mod conference, and we couldn't figure out how to get any decent synergies together yet, at least, because they have a completely different programming framework. They have different design goals. But if anybody has any ideas, we're obviously open to any suggestions and always interested in building cool and interesting new things. I hope that kind of answers your question. Other questions? We'll assume everybody is super fascinated with the workbook and is playing around.
Take the time you need. And I'm not sure if you have my mail address or any mail addresses, but I can post it in the chat. So if you come up with problems afterwards, you can just ask.
Also, I'll put the GitHub repository in the chat, and if you find any problems or have questions, just open an issue. And you don't even need to write any emails. Yes?
Hi, I'm Christina, and I'm with the Klima dashboard. I'm not sure if you heard of it, but we're basically trying to visualize data for end users to better understand climate data.
Yeah.
And I think it would be really interesting for end users to have some kind of GUI, and we might even be interested in collaborating if you're if you don't have any concrete plans yet. Just saying. Sorry. Go
we
ahead.
have multiple project applications running about developing a GUI, but that I think is non-exclusive to not also working together with you and having some kind of building simulation tool. But yeah, we can talk offline about it in more detail.
Yeah, sure.
That would be nice.
I'll also drop the link for the dashboard if you're interested.
Mm-hmm. Looks super nice and fancy. You have good designers. Since it looks like there's no more questions and the plenary session starts at 10:30. Yeah, I think we can close now. Thank you all for coming. Hope it was interesting. If you have any questions or any feedback, open an issue on GitHub or write us an email. And yeah, have a very nice weekend then, or rest of the conference first, then a nice weekend.